Mars yard here at JPL. Why are we here? Well, just recently, today in fact, NASA gave the go-ahead, the green light to begin building the next Mars rover. This rover will be launched in 2020 and will land on Mars in 2021. So we're calling it the Mars 2020 rover. And so today we thought it might be a good idea to have a Facebook Live to introduce you to the mission and also to the scientists and the engineers. We're going to do a couple of things today. We're going to give you a tour of the Mars yard. We're also going to give you a tour of a lab where we're doing drilling and caching, and we're also going to be taking your questions. So be sure to go ahead and put your questions in the comment section if you want us to answer them later in the show. Before we get to our scientists, I want to give you a little bit of a tour of this place. We're going inside what we call the shed here at the Mars yard. It's kind of a garage for none other than our Curiosity rover. This is an exact replica of the Curiosity rover on Mars. It has basically everything that our rover has on Mars except for the power source and the laser. But everything else is here. And we use this to test out software, the arm, the cameras, everything we want to check out before we actually send those commands up to Mars. So this is the actual Curiosity test rover. A little bit later on, as I said, we're going to be going to the test bed for drilling and caching, and I'm also going to be taking you outside to see the Mars yard. But before we do that, I want to introduce you to someone. This is Ken Farley. He is the project scientist of the 2020 mission. And Ken, why don't you go ahead and fill folks in on what 2020 will be all about?
Good morning. Welcome to the Mars yard. This is a very appropriate place for me to talk about the Mars 2020 mission because the Curiosity rover is very, very similar to the rover that we are going to use for our mission. I'm going to tell you a little bit about the rover in a few minutes, but first let me give you some details about the mission. As you just heard, NASA has given us the go-ahead to complete development of the mission. This is a really big and important step for us. And we are going to develop the mission and we're going to launch in August of 2020. We're going to land in February of 2021, and we'll explore the surface of Mars for at least 2 years. While we're there, the major scientific objective of the mission is to seek the signs of life. Of course, one of the great questions that people have wondered about for a very long time is, are we alone? Is there life beyond Earth? This question has, I think, become much sharper recently with the realization from many, many observations that planets beyond our solar system are common. An enormous number, thousands and thousands of exoplanets have been discovered. And so for me, this question is no longer, is there life out there? But is it really plausible that there isn't life out there? There are so many places it could be. Well, one way to approach this question is to go to somewhere beyond Earth where we think life could exist and see whether it's actually there. So this is what motivates the Mars 2020 mission. We're going to go to Mars, and the reason we're going to go to Mars is we believe within our solar system it's probably the most habitable place, or was the most habitable place. So let me explain that. Presently, the surface of Mars is very cold, it's very dry, and it has a lot of radiation. The surface of Mars is not conducive to life as we know it. But if we look at the rocks, we can see that it used to be very, very different. Billions of years ago, there were rivers and there were lakes on the surface of the planet. And one of the most important discoveries that Curiosity made early on in its mission is contained within those rocks is evidence of an environment that had all of the conditions that we believe are necessary for microbial life. We found a habitable environment. And this really raises the question then, if there is a habitable environment, did life evolve there? Did it thrive there? Now, this life has almost certainly disappeared because the climate changed. About 3.5 billion years ago, it stopped being warm and wet and turned into the cold desert we see today. So we're going to focus our exploration on this time in the distant past. So we're going to use a version of the Curiosity rover. That's going to be the platform that we are going to start with. And we have to make a few modifications to it. Now, the reason we're going to start with Curiosity is that it is a very, very capable feat of engineering. It's really a remarkable tool. And this allows us to focus our resources, our time, our money, and our engineering talent, developing the capabilities that are necessary for our mission. So let me show you on this drawing where our instruments are going to go and what they're going to do. Located here on the mast, we'll have a high-resolution stereo zoom camera. This is capable of producing images both near and far, and will allow us to produce panoramas very similar to those that we get from Curiosity. These are really spectacular images. We should be able to do the same with that camera. Also mounted on the mast is a laser. This laser will fire at rocks in the near distance, and the signals that come back will tell us not only the elemental composition of the rock that we hit, but also the mineralogical identity that we hit. So this will allow us to come up with a really good understanding of the geologic environment that surrounds the rover. Now, when we want to study rocks that are closer up, we can deploy the robotic arm, which is mounted here in the front of the rover. Instruments on the end of the robotic arm will allow us to investigate in great detail a piece of the rock about the size of a postage stamp. We'll have a microscopic imager so that we can look at the fabric and the structure of the rock. And we'll also have the ability to map the elemental composition in that postage stamp and identify minerals that are present within it. And one of the most exciting new features is on the rover is that we will also be able to identify and map the distribution of any organic molecules that might be present. And this is important because organic molecules are produced by, among other things, life. So this is one way that we could identify signs of ancient life on Mars. Towards the back of the rover here, below the power source, we have a ground-penetrating radar. This will allow us to investigate the structure of the rocks beneath the rover down to a depth of a few tens of meters. So we can look at the rock layers that we can't see with our eyes, and we can also identify whether there are any unusual features like ices and brines, which would, of course, be very interesting. Then, mounted on the deck of the rover and also on the mast are a suite of instruments that comprise a weather station. So we have the ability to measure temperature and pressure, humidity, wind speed, and also assess the dustiness of the atmosphere. So this allows us to further characterize the current environment on Mars. And finally, the last instrument that we have is entirely different. Its purpose is to further NASA's journey to Mars by actually testing a technology that would be of great value for future human exploration. And in particular, we're going to fly a device whose purpose is to demonstrate the conversion of atmospheric carbon dioxide to oxygen. So this is an example of in situ resource utilization. Of course, oxygen would be of great value to future human explorers, both to breathe and also for their rocket to bring them back to Earth. If they don't have to bring all that oxygen with them, it makes the mission much simpler to do. Finally, one major change that we have to make to the rover is to include a system which is capable of preparing samples that we could bring back to Earth in the future. We're going to prepare about 35 samples of core that we take from the rock and seal it up. And the mechanism for doing that is located, drill on the robotic arm, and an assembly in the front of the rover. And you're going to hear more about that in just a few minutes.
All right, Ken, so we have a couple of questions for you. Let's begin with Juana's question, and it's this one. About the new rover, what energy source will be used in it? Will the energy last a long time?
Yes, the energy will last a long time. The energy source for the rover is mounted in this region back here. It's a nuclear power source, and it will last at least 10 years.
All right, here's another question. This one's from Will. Can it dig? Excavation, like damaged wheels digging ruts into the ground. These can truly uncover wonders.
Yes, we'll have the capability to use the wheels to form trenches and allow us to see what's below the surface of loose material.
And Stanley asks, will a 3D printer go on the next mission?
We will have no 3D printer. I'm sure that we will be able to, with our complex set of instruments, we'll give you some rich information. You don't need a 3D printer.
All right. From Shane Allen of Tribune Media, what we think alien, we think of things that look nothing like what we see on Earth. Are any of the potential former microbial life you think you'll find similar to what we have on Earth, or will they be completely different?
This is an excellent question, and we just don't know the answer. We are going on the assumption, because it's all we can do, is to assume that life will be like life as we know it. And so we are imagining it will look like terrestrial microbial life. But of course, we're out there to discover things. And especially if we bring the samples back to the lab in the future, I think we'll learn a lot about that question.
A question from Edward Cox of CPP Writer. Would it be possible for the next rover to carry a compressor and storage cylinder to compress Martian air and a distribution system that would enable the rover to clean its camera systems, surfaces, etc., of accumulated dust?
Well, interestingly, we haven't had very much trouble on Curiosity with the accumulation of dust, and we don't expect major problems with the Mars 2020 camera systems. But we are bringing a device that will clear dust, in particular to clear dust off of the rock surfaces, because they will be covered with dust. And so we'll have what we call a puffer. Basically, it will blow compressed air and blow the dust away so that we can look at that postage stamp sized piece of rock that I mentioned.
All right. From Murat, and forgive me if I don't pronounce this name correctly, Yurtumats, from Medium, is it possible to use Zeppelin-type vehicles to carry rovers from one place to another? Is the atmosphere sufficient for this?
I'm not an expert in this area. I haven't heard much discussion about that, but we won't be able to do that.
All right. From Tim Sassoon of Film Design, and you're going to have to help me with this one too. Where and how did Mars acquire enough free oxygen to turn the planet red?
This is another great scientific question. So Mars is red because the surface is essentially rusty. It's got oxidized iron. The question is, where did the oxygen come from to do that? And I'll just tell you one hypothesis that's out there, and that is that water that was in the atmosphere before there was oxygen, the water was actually broken down by interaction with light, and the hydrogen was lost to space and left the oxygen behind.
Another social media question from Sean. Does it have a selfie stick?
Yes, we will produce selfies. I'm not going to tell you how it's done, because even on the science team for Curiosity, we wonder how it actually works, but we will be able to do the same thing.
From Han, the question is, does Mars have seasons?
Yes, absolutely. Mars has seasons, and they are there's larger variation than terrestrial seasons. This is very important for us because it gets very hot in the summer and it gets very cold in the winter, and we have to design accordingly.
Ashu asks, when will it be launched?
There's a relatively short window of about 30 days in August of 2020. If we don't make that launch, we have to wait 2 years. So we are working very hard to make that launch.
Valerie wants to know, what is the rover's name?
So one of the important things that goes along with this go-ahead that we got from NASA is that NASA will begin the process of engaging the public in coming up with a name for the rover.
From Sami, can we make oxygen on the surface of Mars?
Yes, we can, and that's what this instrument that we have, which is called MOXIE, is going to do. It's actually going to ingest carbon dioxide from the atmosphere and react it and produce oxygen.
From Len, the question is, does the new rover have a laser like Curiosity, and how does the laser work?
Yeah, we have a laser that is similar to Curiosity's but better. The laser is mounted up on the mast, and it fires high-energy laser light at the rock, and it actually causes that rock to vaporize. And when that vapor cools down, it emits light that comes back to the rover that tells us what minerals are present and what elements are present.
Johnny has a question, and it is, if the rover discovers an ancient civilization, will you tell us?
I'll be honest and say nobody has told me what I am supposed to do if we discover that. But one thing I will say is that we will be taking the images just like Curiosity does, and the images will almost immediately appear on public websites. So you're all along for the ride, just like us.
Aaron has a question. What kind of organic molecules do you hope to discover?
Organic molecules are complicated because some might be associated with life, but many others are not associated with life. So one of the key things that we have to do is sort that out. So we will be, in our seeking the signs of life, we will be looking for specific patterns of molecules that are present.
Jonathan wants to know, will there be a 3D camera?
So we have a stereo camera, and the stereo camera allows us to make 3D maps of the surface and then overlay the imagery on top of it. So it will essentially look like a 3D image.
Here's a terrific question. I imagine it may come from some of our summer interns here at JPL. The question from Aaron is, will interns get a chance to work on this project?
Yes. We have interns now, and we will continue to have interns over the coming years.
Okay.
They're an important part of the effort.
Absolutely. Adelina, will this be searching for more evidence of water?
So I think at this point, it is very clear that Mars had water, and I wouldn't necessarily say we are searching for the water. We know where to go to find it. There's a lot of data that tells us where to go. Once we're there, we will specifically be looking for regions that would have had water in them. But that's going to be one of the important factors in our selection of landing sites.
All right. Well, that's all the questions we have for now. And we will be checking in with Ken again later on when we come back here to the Mars Yard. Meantime, we're going to head over to Matt Robinson. He is over at the Mars sampling area. This is, a couple of feet away from us, a couple of buildings down from us here at JPL. Matt will be coming back here and also answering your questions. So be sure to put your questions in the comment section here on Facebook Live, and we will be sure to keep those questions for Matt when he joins us. Meantime, we will also be giving you a tour of this. We can pan over there, I'm not sure. Ooh. No, we're told not to because it's probably too bright out there. But we will be also giving you a tour of the Mars Yard and where we drive some of our rovers and do some of our testing. But meantime, we're going to go over to see Matt. He's in the test lab. It's the sampling and caching lab. He's the deputy manager of that, and we're going to go to him now.
Hi, I'm Matt Robinson. I'm the deputy manager of the sampling and caching subsystem on the Mars 2020 rover. Welcome to our sampling development test bed. I'm here today to talk to you a little bit about what we're doing up here and show you around. Our team, my team, is tasked with acquiring samples for the Mars 2020 rover and processing them for potential future return. So in terms of the sample acquisition part of it, what we have a coring drill on the end of a 5 degree of freedom robotic arm. A coring drill here is one of our prototype drilling bits. Right here I have a small model of the robotic arm, what the robotic arm will look like. It has 5 degrees of freedom, or joints. There's a shoulder azimuth, an elevation joint, an elbow, a wrist, and a turret. The coring drill is mounted on the end of the turret. This allows us to position the drill anywhere in front of the rover to acquire samples. Once we place the drill on the surface, we have 2 modes for drilling into the surface. We have a percussive mode, a rotary percussive mode. Think of that as operating a jackhammer, where the drill will actually jackhammer into the surface as it rotates. We also have the ability to drill into the surface in a rotary only mode, and I'll talk about that in a minute. The act of doing that stores the core up into the drill inside of a tube. Once we acquire the sample into the tube, we retract the drill from the surface, move the arm up, and we move over to the rover to the caching portion of our subsystem. Stepping over here, we'll take a look at what that looks like. The caching system starts out with the bit carousel. So the robotic arm moves up and it docks with the carousel. When it does that, it takes the drill bit with the now filled tube and it drops that off into the bit carousel. The bit carousel then rotates around, and there is a smaller planar robotic arm within the caching system. And the robotic arm moves over to the carousel and it pulls the tube out of the bit. Then, within our caching system, we have a number of stations that will process and prepare the tube for potential return at a later date. In terms of the preparation, we have a camera on board, so the robotic arm, the small robotic arm, moves over and to a camera station, and we take a picture down the tube to see what we have inside. Then we go over and we get a seal, and we put a seal on the top of it, and we hermetically seal the tube. Then we go over to the storage location on board, and we insert the tube into the storage location. Once we acquire a number of samples, say 5 or 10, we'll then look for a nice parking location on the surface of Mars, and we'll drop off our 5 to 10 samples into a nice little pile so a potential future rover could pick it up for potential return. As I mentioned, our coring drill is there to acquire core samples, but it has other functions. Wait, there's more. One function is for abrading the surface. In our bit carousel, we have an abrading bit. What's that for? On our turret, we have our instruments, Sherlock and Pixel, science instruments for doing science observations. Well, if you take a look at a rock, the rock is, an unprepared rock surface is very weathered. Our abrading bit, we can use that to abrade away the first few millimeters of the surface. And if you zoom in, you'll see that what does that give you? It gives you the very nice fine-grained detail that the science instruments Pixel and Sherlock like to see. We also have a regolith sample acquisition device. Regolith meaning loose soil. So what we would do there is we would go over to our bit carousel, and we would drop off our coring bit into the carousel, and we would pick up a bit like this. Then we would dig the tool into our regolith, and as a result of that, the soil is going into the bit. And we'll also have a tube on here where the sample will be collected into the tube. Now, we're standing here in our rock room, what we affectionately call our rock room. One of the exciting things about working on a Mars mission is we don't quite know what we're going to see. So we have to be prepared for a wide range of contingencies. So we've identified a number of rocks, a suite of rocks, if you will, to test. On the harder end, we have our basalts. The challenge of drilling into a basalt is just penetrating into the rock without wearing out your bit. But when you're done drilling into it, you get a nice, fairly solid piece of core. On the other range, we have our mudstones. Our mudstones are very interesting scientifically, but they're fairly soft. When we drill into those, we tend to end up with core samples that break up a little bit more. The challenge there is not drilling into the sample, but it's retaining the sample. Now, even though this core is broken up into little pieces, it's still very, very scientifically valuable. We also have the two different modes for drilling into those. As I mentioned, for the harder rocks, a percussive type of motion would work better. And for the weaker rocks, a rotary only to try to make a solid piece. So let's take a look and let's step into our development test bed, and let's take a look at what our test bed looks like. This is our environmental development test bed, or EDT. It allows us to test our coring drill in a Martian relevant environment at Martian pressure and Martian temperature. Right now we're in an open chamber orientation for doing checkouts and for our demonstration today. But when we want to do Martian pressure and temperature, what happens is this lower part is mounted on a hydraulic lift. And then what we'll do is we'll lift up, the hydraulic lift will lift up this entire chamber into the above space, and it'll clamp on. Then we can pump down to Martian pressure and Martian temperature. Martian pressure is about 1% of Earth atmospheric pressure, and it actually does make a difference for coring development. If you take a step up here, we're in the middle of a test right now. This is a robotic arm. It's more like an industrial robotic arm with a prototype coring drill mounted on the end of it. Our flight robotic arm will have about the same length, but this robotic arm is not optimized for mass. So right now what we see is our drill is preloaded up against the rock. You can see the stabilizers here. Imagine if you're going to jackhammer into a surface, those stabilizers help stabilize the drill to keep it from dancing around on the surface. We've already done what we call the hole start. Think about if you're going to drill into a piece of wood or into a rock, you would want to start with a pilot hole. And that's what our testbed operators have done so far. They've created a pilot hole. Once you do that, then you'll start coring into the rock. And what I want to do is I want to show you a little bit of video, or show you a little bit of operation of our drill bit. So it'll take us a few seconds for us to start up. The stabilizers themselves, there we go. So what you'll notice is there's powder actually flowing out of the hole. On the MSL rover, we wanted to acquire that powder for delivery to our science instruments. Here, when we're trying to acquire a core for potential future return, powder actually gets in the way. So we want to get that powder out of the hole and move it out so we can continue to core. As we continue to test, we will develop our coring drill. We'll learn from our test data, and we'll further refine it. If you look at the bit, for instance, there's a lot of geometry to the bit. There's the number of teeth on the bit, the flute design that transmits the powder out of the hole, out of the way to continue coring, so you can continue to make progress. So these are all parameters that we, through the course of testing, we use to improve our performance. So that's a little bit about our drill. Thank you for coming by our sampling test bed today. At the end of the segment today, we'll have a Q&A session. I'll be back down into the Mars yard to help answer your questions. Back to you, Gay.
Hi, everyone, and as promised, we're going to show you a little bit of the Mars yard now. Take a look behind me. This used to be a parking lot here at JPL, but then they decided to turn it into a little bit of Mars. They took photographs or images that were sent down by the Viking lander, as a matter of fact, back in 1976. To mimic Martian terrain. And so over here you can see that we have slopes and we have bedrock and we have dirt. And basically over on the north here we have different slopes using bedrock and also soil to create different sorts of challenges for the various rovers, and so we can check out their mobility by driving them on these surfaces. Now, we use this yard for Sojourner and also MER, which was Spirit and Opportunity, but they were able to do a lot of their testing indoors because they were smaller. But this yard has really been put into use after we had Curiosity because it's so much bigger and needs to have so much more space. So this yard has been put into a lot of use over the last few years. With me is Ken Farley again, and the next thing we'd like to talk about is the fact that before we can even consider driving the rovers, we have to figure out a place to land. And just like any other real estate, location is key. And Ken's going to talk to us now about what we're looking for in landing spots.
Absolutely. The most important decision that we have ahead of us
is where we're going to send the rover. It's a complicated decision that we have to make because there are a number of things that have to be true about the landing site that we go to. First and foremost, we have to be able to land there safely, and we have to be able to navigate around on the landscape successfully. We have to stay out of sand and things like that. But we have some additional capabilities, which you're going to hear about in just a minute, that will help us do that. So I'll tell you about what the scientists are discussing. Scientists have been discussing the landing site for the mission for several years now. And here are some of the things that we want from the landing site. We want a lot of rocks, because rock outcrop is what tells us the geologic story. So we're looking for places where there's lots of cliffs and rock exposure on the surface. Those rocks must actually date from this period that I mentioned earlier when Mars was warm and wet. So those rocks must be older than about 3.5 billion years ago. We have an enormous amount of information from previous missions about the surface of Mars, and this has allowed the scientists to narrow down the sites, possible sites, to about 8. And those sites all have characteristics that we believe suggest that they were habitable. And they fall into 2 broad classes of sites. The first half of the sites are associated with surface water. There are things like rivers and lakes and deltas recorded in the rocks. The other half of the sites are associated with high temperature water circulating through rocks. Now, the reason we have been focusing on those 2 kinds of environments is because on Earth, those are areas where microbial life thrives. And we're hoping that the same would have happened on early Mars. So we have 8 sites under consideration right now. And those sites are also being evaluated for their safety and for their traversability, the ability to drive the rover around. Over the course of the next couple of years, we will continue this discussion with a very broad cross-section of the science community, trying to develop ultimately one candidate landing site. Now, I mentioned one of the key things for us is to land in environments that have a lot of rocks, and rocks are challenging for landing. But fortunately, we have some new capabilities with the landing system that will allow us to get into this very tricky terrain. And to hear more about the entry and descent landing process, the most exciting moment of the mission, I turn it over to Al Chen.
Thanks, Ken. You may remember how Curiosity landed with its 7 minutes of terror, and we're using that as kind of the starting point for Mars 2020. We start off hitting the atmosphere at over 11,000 miles per hour and come tearing through and decelerating at up to 10 Earth Gs, while experiencing a lot of aero heating as we go through. We're also firing thrusters to steer our way to the landing target. Once we get down to about Mach 2, or about 900 miles per hour on Mars, we deploy the supersonic parachute, drop off the heat shield, and prepare for power descent. Once we get down to that area, we cut loose the parachute, fire up those rocket engines, and head down to the ground, and end with the sky crane maneuver, much like Curiosity did, landing the rover right on its wheels. So from the outside, things look pretty much the same. But under the hood, we made a number of improvements that will help us get to the types of sites that Ken is talking about. The first such change is range trigger. Back with Curiosity, all it could do was deploy the parachute based on the velocity, upon hitting a certain velocity, and then deploy the parachute when we got to that velocity. In fact, Curiosity actually knew that it was a little bit past the parachute deploy target when it deployed the parachute, but it couldn't do anything about it. All it was doing is waiting for the right velocity to pop that chute. Here with Mars 2020, we're giving it the smarts to choose to deploy that parachute based on where it is, so that if it's coming up a little bit short of the parachute deploy target, it can wait a little bit longer to deploy that parachute. Or if it thinks it's going long, it can deploy the chute a little earlier than it normally would have. That allows us to shrink the area that we could be coming down in, the landing ellipse, the uncertainty of the places where we could land, by about 50% in area. So that helps us land in much tighter spots that we couldn't have considered before with Curiosity, and also lets us land closer to the types of things that the scientists want to go see after we land on the ground. The second major change that's happened with the entry, descent, and landing system is the addition of something we call terrain relative navigation. On Curiosity, once we popped the heat shield, we took pictures of the ground with a camera, but we didn't use those for landing. Those were just used after landing to see how things kind of went. This time, we can use those pictures and take them as we're going down on parachute and match them up with an onboard map, a map that we've put together using pictures from orbiters. Just like you or I can kind of take a look around and match up what you see with an onboard map with a map and figure out where you are. Mars 2020 will be able to do the same thing. Once Mars 2020 knows where it is by using those pictures, it can then avoid hazardous terrain that's nearby. For previous missions, we've had to push all these kind of hazardous terrain, which is what the scientists actually want to see. It's things like big slopes and scarps. You know, we prefer landing on things that are flat. The rover wants to land wheels down on flat places. So we've had to push all of these interesting features to the scientists outside the landing ellipse. They keep telling us that flat is boring, but the flat is safe for us. But this time with TRN, we have the ability to have some of those things in the ellipse, because once we have those pictures and know where we are, we can avoid those dangerous spots. That allows us to put the ellipse in places where we couldn't have considered previously. We were always looking for flat, boring landing strips. Now we can look for places that have patches of flat things along with all these science targets nearby. That means getting to sites that we couldn't have considered before. In fact, some of the sites that Ken was talking about, some of those 8 sites, were sites that were rejected for MSL because they were unsafe. Now we can consider landing in those with the addition of terrain relative navigation. That also helps us land closer to those targets when we get on the ground. We don't have to drive as far out to get to these places that would have been dangerous before. Another thing we're adding that I'm pretty excited about for entry, descent, landing doesn't help us land, but will help us kind of see what it's like to be with the vehicle as it's going through the entry, descent, and landing process. And that's the addition of a suite of EDL cameras. So we've never actually seen a parachute inflate supersonically at Mars. This time out, we'll have a series of cameras looking up at the parachute, so we can see the parachute in the process of inflation, and then as we ride it down toward the ground. We'll also have a descent camera, so we can see the ground rushing up towards us as we head down toward the ground. And we'll also have a couple of cameras on the descent stage, that rocket jackpack that lowers the rover. And looking up from the rover, we'll have another camera looking back up at the descent stage. So these two cameras, kind of looking at each other, will catch us in the act of sky crane. We'll really see what it's like to be there while we're actually putting this rover down on Mars in 2021. So I'm pretty excited to land safely and get that video back after we land and see what it was really like to be on the vehicle as we went through EDL.
All right. Well, we have some questions for you. The first one is a social media question. It's from Johnny, and he asked, to what extent is the rover controlled by humans, and what extent is it AI? Who wants to take that?
I guess I could start with that question, to what extent it's controlled, at least for entry, descent, and landing. It's not at all controlled by humans during the active landing. In fact, by the time we find out whether it's made it or not, it's already happened, right? The vehicle has to take care of itself as it's going through EDL. So we have to program it so that it makes all the decisions on the fly.
Okay.
Once we're on the ground, I guess we can talk about the surface here. Let me pass it again.
Yeah, I think it's worth pointing out that one of the things that is very challenging for us in this mission is to work efficiently on Mars. And because of the long delay of communications, we have to be able to have autonomy on the rover. So we're investing a lot of time to allow a lot of time and effort to allow the rover to use its computer and its autonomous systems to navigate and to do science. So this will be an important step forward in remote exploration.
Question from Yodam. Curiosity has had damage done to its wheels due to sharp features on the Martian terrain. What improvements have been made to the new rover's wheels?
Okay, I'll take that.
All right, I'll take that question. So the question was about what's going on with the wheels and what are we doing with Mars 2020 to reduce the damage. We are looking at a new design of the wheels that should help mitigate that, which principally has to do with thickening the wheel so that it's more robust to kind of those puncture type of concerns that we've had with Curiosity.
Maybe this is a question for Matt. This is from John. Can the rover go drop a probe into one of the big lava tubes? A probe.
Carry a probe? Well, we're not carrying any probes with us on this mission, so there are no plans to in the current baseline.
And a question from Amy. Can the rover repair itself?
The rover can't repair itself per se. However, with our sampling system, we have to have a number of things to be prepared for contingencies. In our bit carousel, as I described earlier, we have a number of spare drill bits. Those are for a number of contingencies. One is as we drill into harder rocks, the bits will wear out and we can replace those bits with other bits. Another is if we're drilling into a rock in a challenging orientation and if the rover were to shift and the bit gets stuck in the rock, we can jettison that bit and go grab another one. So that's one of the ways that we don't have a repair capability per se, but we have contingencies in place to adjust for things like that.
Just to follow up on that just for a minute, because I think it really drives home the challenge of this mission and all missions on Mars, is that nobody can go and fix what's there. So the engineers, these guys, have to think of all sorts of things that might go wrong and figure out ways to prevent them from happening, and if they do happen, how to recover.
A question from Marta. Is water on Mars toxic?
There is no reason to believe that the water on Mars per se is toxic, but we believe, based on measurements that were made by previous missions, that there are chemicals that might be in the water, like perchlorate, which would not be very healthy for us and for life in general.
Question probably for Matt. What is the drill made of? The drill.
The drill has a number of materials that we use. The bits themselves are made from steel. The teeth are tungsten carbide, and the rest of the drill is a lot of titanium and some aluminum. So those are the types of materials we use.
And from Marina, the question is, how deep can you drill?
We can drill roughly 10 to 15 centimeters into the surface.
Question for probably Ken. Will you perform analysis on site on Mars? Any analysis?
So we have a collection of instruments, indeed, that will make analyses. I told you we'll be able to measure the elemental composition of rocks with the laser off in the distance, and also we will be able to look at the postage stamp sized piece of rock and characterize its elemental composition and its mineralogy. So yes, we will be making analyses on Mars.
Maybe this is for Al. Ruby wants to know who will control the rover and how is that done? The overall control of the rover.
The overall control of the rover and the mission is done from here at JPL, from different control centers that are located on lab. During cruise, of course, cruise and EDL, we control the whole vehicle as it's going out there and send up commands. And then on the surface, we have our rover drivers, of course. And I don't know, Matt, if you want to talk to that some more about what goes on a day-to-day basis there.
Oh, sure. So we have a team of engineers, the rover drivers, who work with the scientists like Ken to identify the activities that we want, to identify a target that we would want to acquire a core sample from, for instance. Then the next step is for the rover driver to plan out those activities, to take those high-level plans and make them into a sequence of commands for the rover to execute over the day. Then we go through a number of checks and upload that plan to the rover. And then the next day you find out how it did.
All right. We have a question from Abigail. How do you land the rover without damaging it?
Landing the rover is, of course, very tricky, right? There are lots of places where things can go wrong. So the whole theory behind the sky crane really is to touch the rover down at the types of loads that it sees when driving around on Mars. So that means we touch down very softly. We touch down at about 1.5 miles per hour, right on the wheels. And that's how we do it, right? We know this is a precious thing that we want to preserve its safety for the mission ahead of it, which is pretty long. So we try to be very careful about how we place it down in safe spots that we can find.
Adele, how long does it take for a signal to travel between Earth and Mars?
The signal, signals travel at the speed of light from Mars to Earth and back, and that can vary from, in the 5 to 25 minute range or so, depending on where we are in our respective orbits.
And a question about the camera. How far can the camera zoom on the 2020 Mars rover?
We're probably talking about the surface cameras, so let me throw that to probably Ken here.
I don't know the technical specifications, but this will allow us to use them in a way that is similar to binoculars.
Okay, and then from TJ Johnson, how much of the planet will the rover cover in terms of traveling?
So this is a very important question. It depends on where we land, and if Al does his job properly, we will land very close to the scientific targets that we will spend most of our time on. But we're designing to be able to drive at least 10 kilometers across the surface.
All right. This is probably a question for Matt. It's from Aaron. Will the rover be capable of changing drill bits? I think you mentioned that.
Yeah, absolutely. It will not do that autonomously. The planners will decide when they want to change out a drill bit, but we will absolutely have that capability.
And Zach wants to know, also for Matt probably, does the drill bit clean itself out so the samples don't mix?
Oh, that's an excellent question, actually. The tubes themselves are one tube per core, so we have a pristine tube each time we acquire a core. Now, the bits themselves are used for multiple drilling operations, so there would be a little bit of dirt that might stick to the bit themselves. But we do have some ways to clean it. As we saw earlier, the percussion environment is pretty strong, so we can point the drill off to the side and we can percuss it in air to help clean it off.
Okay, well, David wants to know, that looks like it might take a lot of power. How often can you drill?
Well, from drilling, because we have to drill and then process the sample. So the drilling itself, we would drill one sample per day, and then 1 to 2 sols to actually process. Sols are Martian days to process the sample, to go over to the vision station and take pictures of it, to seal it, to actually take measurements of it. So we could drill if we wanted to every day, 1 drill per day. But likely every few days we would drill.
And Alan, maybe this one's for you. It's from SM. How much time does it take for a rover to reach Mars?
That's a great question. So right now we're looking at launching in mid to late July of 2020 and arriving in mid-February. So we're at about 7-month cruise between launch and landing. That does vary depending on where you go, but for 2020 it's about 7 months.
For Ken, this one's from Brian. What kind of weather does Mars have?
Well, you wouldn't recognize the weather on Mars as similar to Earth, but as we talked about earlier, it has seasons. So there are seasonal fluctuations in the weather. The winds change, the temperature changes with the season. It also changes over the course of the day. And from a practical point of view, the temperature variation from the nighttime to the daytime is very, very large. And one of the challenges this presents for the rover itself is as the temperature changes, the components expand and contract. And this causes all sorts of alignment issues that we have for making the science observations. So this is an important thing that we spend a lot of time thinking about.
All right, from Alan, to land the rover more precisely, are we going to need GPS on Mars?
I'd love to have GPS on Mars. Unfortunately, we don't have the GPS satellites over there, and the signals from here don't quite get that far. So we're doing navigation in a couple different ways, right? We're using deep space network-based radiometric navigations. That's kind of looking in your rearview mirror as if to navigate your way there. That kind of gets us started, and then we use gyros and accelerometers to kind of dead reckon our way through the atmosphere until we get down to heat shield SEP, when we get a look with the radar that tells us how high we are. And that's where what I was talking about earlier, terrain relative navigation jumps in here. Suddenly we can take those pictures and figure out where we are. On Curiosity and without terrain relative navigation, we'd be looking at uncertainties of our position of up to 3 kilometers, 2 to 3 kilometers. With terrain relative navigation, we can get that down to tens of meters. So that really helps us figure out where we are.
Well, this one is kind of a design question. It comes from Gerald. Talking of the Mars rover, has anyone considered using a track vehicle? Yes, I know it'd be heavier, but would have to be designed so the tracks don't fall off. But has anybody thought of that instead of wheels?
Do you want this one, Matt, or I can take a shot at it if you want? I mean, certainly we've looked at tracked rovers, tracked mobility systems before. It has been considered. There are a number of pluses and minuses to those types of approaches. I don't know if we want to get into that in any more detail, but certainly it's been looked at before.
And would it be much heavier if we went in that direction?
I don't know the details of that, actually. I suspect it might be, but I don't know.
Potentially.
Yeah. There are different ways to go about that as well. So.
And it may affect the size of the rocks that you can drive over. One of the great things about our rocker bogie system is that we can move over rocks that are up to 1.5 times the wheel diameter. which from a traversability aspect, that's actually huge for a mobility system.
And we have covered this a little bit, but just to reinforce it, this should go to Ken. What is the main mission of this rover?
So as I said, the central scientific objective is seeking the signs of life and preparing this collection of samples for possible future return to the Earth. The possibility that samples will come back in the future is very exciting to the science community, because the kinds of observations you can make in a laboratory are enormously more diverse. And so we're taking the first step that the science community has wanted to be taking for a long time.
David wants to know about the camera. What kind of resolution are we talking about? 1080p? Are we talking about 4K? What are we talking about?
I don't know the details.
We, of course, have lots of cameras on board the rover. Let me talk to the EDL cameras right now. We are talking about 1080p cameras. We will be seeing color video once we land successfully and return that video. We'll have pretty high frame rates. For the parachute camera, we're looking at frame rates upwards of 100 to 150 frames per second. And then for most of the other cameras, we're looking in the 30 frames per second or so video quality. I don't know if anyone wants to talk to the surface ones.
So one of the great things about a rover is just the number and variety of cameras that we have. We have our RSM mass-mounted cameras that we can use for navigation, and our mass cams for zooming in on the surface. We also have a camera called Watson on the end of the robotic arm, which is a very high-resolution camera. So not only does it have a lot of detail, you can get close up to surfaces. So you can move the camera closer to your targets. So for those types of observations. So all kinds of cameras, really great color images that we can acquire.
From Lance, he has a question about how does NASA prevent Earth-based microorganisms contamination of Martian samples, especially those microorganisms that are resistant to radiation that may make it into the clean room?
This question really goes to the heart of the science that we hope to do. We wish to look for signs of life, and one obvious sign of life is cells. And we have it is necessary for us to absolutely sterilize all of the material that will come in contact with the samples. So, for example, the sample tubes which you heard about, they're actually going to be placed in a container and taken up to 350 degrees centigrade in air to burn off any living material that was there. We're spending a lot of time making sure that we don't have what we call round-trip contamination.
This is for Matt. How do they sterilize the drill bits on Mars? Sterilizing the drill bits.
Okay, so we don't sterilize the bits on Mars. We sterilize them on Earth before we package them up. So we have an entire process of things like dry heat microbial reduction, baking out the bits to kill all the microbes, and also contamination to get rid of that. We will install those bits. That'll be one of the very last things that we do before we launch the vehicle, so that we don't contaminate them in between cleaning them and launching the vehicle to Mars.
From Dominic, the question is, how heavy will the Mars 2020 rover be? How heavy?
Right now we're looking at landing 1,050 kilos for Mars 2020, which is about 150 kilos heavier than Curiosity was.
All right. Question regarding the bits again. What if all the drill bits are used?
So in terms of our number of bits, we have on the order of 4 to 5 drill bits. We will acquire about 42 core samples. So we are limited in terms of the number of samples that we can acquire. And the life of those drill bits are designed to match the number of core samples that we can acquire. So we're not in danger of wearing all of our bits out before we can acquire all of our samples. And that's one of the great things about our testing, is to ensure that.
Colin wants to know, is there a possibility of using drones in Mars if in the atmosphere that's present?
We have been asked to study the possibility of bringing a helicopter along with us, so this is under consideration by NASA. But Mars 2020 is not yet certainly going to be flying a drone.
All right. Question from Dominic. So the new rover is not depending on solar power?
The new rover is not depending on solar power. We have a nuclear power source with us.
Okay. From Ron, will a microphone be added to this mission?
Oh, excellent point. I should have mentioned that earlier. Not only is there going to be a microphone, there will be several microphones. So Al mentioned the camera system that we have on the during EDL. There will be a microphone as part of that. And we will also have a microphone on one of the science instruments that will allow us to hear sounds on the surface as we are driving around. So we'll have the first sounds coming back from Mars.
From Leah, how do you plan to return samples from Mars?
The objective of the Mars 2020 mission is to prepare a very compelling set of scientific samples and leave them on the surface of Mars for a possible future mission to go and get them. The decision whether those samples come back is up to people of the future, NASA of the future.
Are there any concerns about the dust that's being kicked up from the retroburn during the crane maneuver?
Yeah, so we were actually just talking about that earlier today. I think we have a pretty good handle on what happens with the engines kicking up material. So we've asked the rover to make sure that they're prepared to deal with the type of kind of debris that could be flying back at us. But we think we have a pretty good handle on that and its impacts on the rest of the system.
We have a couple of questions here asking, when do you think we will be seeing humans on Mars?
The journey to Mars will be a long one. Certainly, we've got a lot of a lot of efforts across NASA looking at how we're going to put people on Mars. So it's certainly ahead of us in our future, and I hope it comes soon.
Okay. Well, we have one more question because we're running out of time, and it's a key question. They want to know how students can get more involved with this mission.
Well, so the interesting thing about this mission, maybe all missions, is they last a long time. So people that are young now can participate in this, especially if and when the samples come back. So I think there are opportunities on the science side to study planetary science and that sort of thing, as well as the kinds of science that we will do on samples when they come back. And there are certainly opportunities on the engineering side. Maybe Al can say something about that.
Yeah, certainly, as many folks know, we have a very robust summer hire and co-op program where folks come out here to work with us. So we've worked with many students. Of course, they can follow along with the mission on our website at mars.jpl.nasa.gov. Looks like you want to say something here too, Matt.
I was going to mention, we up in our test bed that I took you through, we have a number of co-ops and interns who are actually performing a valuable, critical element to what we're doing. They're actually running the tests and collecting the data that we use to help inform our design decisions. So they're not up there doing busy work. They're doing real critical engineering work, and we really rely on them.
Well, that wraps things up for us. Our thanks to Matt, to Alan, and Ken. And if you would like more information, of course, you can check out the websites. Here's one, mars.nasa.gov/Mars 2020, and also, of course, nasa.gov/Journey to Mars. So that wraps it up for us. Thanks for joining us.